Welcome to The Explainer. I am so incredibly excited you're here today because we are diving into something you use literally every single day, yet probably rarely stop to truly understand. I'm your host, think of me as your exam strategist, and today we're talking about the weightlifter strategy for your Cambridge computer science exams. Whether you're taking syllabus 0417, 0478, 2210, or 9618, you need maximum effort in short bursts. High-mark questions require explosive power, and that is exactly what we are going to build today. Now, think about the complex machinery of human anatomy for a second. We have a brain that processes thoughts, senses that take in the world around us, and muscles that act on those decisions. Well, guess what? The device you are using to experience this explainer right now operates on those exact same principles. Today, we're tearing apart the modern computer, metaphorically, of course, and looking at the raw hardware that makes it tick. But we're doing this with a twist. I want you to imagine two students. First, we have Alex. Alex overloads every exam answer with raw computer science facts, but provides zero analysis. Then we have Sam. Sam rushes, panics, and completely misses the command word requirements on the paper. By the end of this session, we are going to fix both of their mistakes, and yours, transforming those red pen marks into green check marks. Let's get into it. Here's our roadmap for today's session. Number 1, inside the computer's brain. Number 2, fetch, decode, execute. Number 3, embedded systems everywhere. Number 4, connecting to the world. Number 5, sensors and automated control. And finally, number 6, acing the hardware exam. Section 1, inside the computer's brain, architecture and processing. Let's start right at the core of the machine. Notice the name right here, von Neumann. Prior to the mid-1940s, computers were essentially these massive room-sized calculators. If you wanted them to do a different task, you literally had to walk around and physically rewire the machine. Then, John von Neumann introduced this brilliant, absolutely revolutionary concept, the stored program computer. He thought, instead of physically rewiring the machine, what if we stored the program's instructions and the data it needs in the exact same memory space? And what if the central processing unit, the CPU, could directly access that memory and execute instructions in sequential order? This single idea is the bedrock of almost every single device we use today. Now, if our friend Alex got a question about this, Alex would just write, it has memory and a CPU. Boom, 1 mark. But top students use the Peel framework, point, evidence, explanation, link. You have to explain that both programs and data are stored together. Real quick, before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE, to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, let's look at the actual anatomy of this architecture. So what does this CPU actually look like inside? You can kind of think of these microprocessor components like the different lobes of a human brain. First up, you have the control unit, or CU. This acts like a nervous system synchronizer, perfectly managing the flow of data around the processor. Next, you have the arithmetic and logic unit, the ALU. This is the math and logic center. It's doing all the heavy lifting, the addition, the subtraction, the comparisons. Then you have registers. These are absolutely crucial for your exams. Registers are extremely high-speed, tiny memory areas located right inside the CPU used to hold temporary data. You need to know them. The memory address register, memory data register, program counter, current instruction register, and the accumulator. And finally, connecting all of this together are the system buses. Think of buses as the neural pathways of the brain. The address bus carries the location of the data. The data bus carries the actual information itself, and the control bus carries the synchronizing signals from the control unit to keep everything in check. If you want explosive marks on an exam, you don't just list these, you explain exactly how they interact. Section 2. Fetch, decode, execute. The cycle of thought. We've got the anatomy down, so let's see it in action. Look at the flow of the fetch, decode, execute cycle on screen here. This is how the brain actually thinks. It doesn't ponder, it acts in a continuous, relentless loop. It starts with the program counter, or PC, which holds the address of the very next instruction needed. That address travels along the address bus to the memory address register. The CPU then fetches the actual data from memory and drops it into the memory data register. From there, it's moved to the current instruction register so it can be worked on. It sounds like a really complex bucket brigade, passing water from one person to the next, but the shuffling of data happens billions of times a second. To simplify that complex flow for your exam answers, remember that it all boils down to 3 concrete steps: fetch, decode, execute. Step 1, the CPU fetches the instruction. Step 2, it decodes it. Now pay attention here because instructions are made of two parts: an opcode, which tells the CPU what operation to do, and an operand, which is the actual data to apply it to. Finally, step 3. The control unit sends out signals to execute the task, over and over and over again. This is where our student Sam usually messes up. Sam rushes and misses the command word. If the exam says describe the execute phase, Sam will just write it executes. No, you have to talk about the control signals. Fun fact, if you overclock your computer's system clock, you're literally forcing this 3-step cycle to run faster than the silicon was designed for. That's exactly why things overheat and crash when the steps fall out of sync. Section 3. Embedded systems everywhere. Specialized reflexes. Now that we know how the core brain works, let's zoom out to the macro level. Not every computer is a fancy laptop or a smartphone. Many are hidden in plain sight, acting as specialized reflexes for other machines. We call these embedded systems. They are specific combinations of hardware and software designed to do one single task perfectly. Think of the anti-lock braking system in your car or the timer circuit on your washing machine. Let's do a quick interactive workshop challenge right now. I'm going to put 60 seconds on the clock in your head. Scan this data table. What is the core trend when you compare the benefits and drawbacks? All right, time's up. The core trend is that while they are incredibly fast, highly reliable, and very cheap to mass produce, there is a massive drawback regarding sustainability. Because the microcontroller is often baked right onto a single chip with its memory and its inputs, you can't easily upgrade it. If the technology becomes outdated or a single component fails, the entire device is usually thrown away. It is a huge contributor to modern electronic waste, which is a great point to bring up if an exam question asks you to evaluate the impact of embedded systems. Section 4. Connecting to the world, input and output devices. Let's transition from the brain to the senses. How did these processors actually know what's going on in the outside world? One of the most common ways computers read the physical world is through scanning. For decades, we relied entirely on traditional barcodes, those 1D parallel lines read by lasers reflecting off the light and dark spaces. But look at the contrast here with modern QR or quick response codes. QR codes are a 2D matrix, read not by a single laser line, but by a camera. Because of this two-dimensional structure, a single QR code can hold over 7,000 digits. Even more fascinating, and this is a huge point for your exams, is that they have built-in data redundancy and error checking. If a traditional barcode is slightly ripped or smudged, it's totally unreadable. A QR code can actually be partially damaged, and the algorithm in your smartphone's camera will still perfectly decode the website link hidden inside it. That's a massive technological leap. Stop scrolling! Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, let's talk about how we physically interact with screens. It feels like magic, but it's pure hardware. There are 3 main touchscreen technologies you absolutely must understand. When you tap your smartphone, you're likely using a capacitive screen. This relies on the electrical properties of your bare finger to change a voltage on a glass panel. Because it tracks electrical field changes, it allows for multi-touch, pinching, and zooming. But have you ever used an older ATM or a supermarket checkout screen where you really have to press hard with your fingernail? That is a resistive screen. It literally pushes 2 layers of polymer and glass together to physically complete a circuit. It doesn't do multi-touch well, but it's cheap and highly resistant to dust and water. Finally, infrared screens use a grid of invisible light beams across the surface. When your finger breaks the beam, it registers a touch. The best part? You can use infrared screens while wearing thick winter gloves, something capacitive screens simply cannot do. Section 5. Sensors and automated control. The feedback loop. Now we reach the absolute coolest part of hardware, true automation. How do computers act without us pressing any buttons at all? They use sensors to read physical properties, like temperature, light, or magnetic fields. But before we look at an example, I want to clarify a crucial distinction. This is challenge 2. Find the flaw. So many students lose marks by confusing a monitoring system with a control system. A monitoring system simply watches data and alerts a human. Think of a hospital heart monitor. If the heart rate drops, an alarm sounds to alert a nurse, but the computer doesn't automatically administer medicine. A control system, however, actively alters its environment based on the data. It uses mechanical muscles called actuators, like motors, heaters, or valves, to physically change the world. If you write that a greenhouse monitoring system opens the window, you just lost the mark. Monitoring just sounds the alarm. Control opens the window. Let's do a speed writing challenge right here. Look at this chemical plant control system. You've got 30 seconds to mentally draft a perfect peel paragraph. Ready? Here's how it works. The temperature and pH sensors are constantly taking readings. But remember, sensors read analog data, continuous, real-world signals. The computer brain only speaks digital, binary, zeros and ones. So the signal must pass through an ADC, an analog to digital converter. The microprocessor then compares this digital reading to its pre-stored parameters. Let's say the acid level is too low. The computer sends a digital signal out. This signal passes through a DAC, a digital to analog converter, which operates an actuator to physically open a valve and release more acid into the mix. This constant, relentless cycle of reading, comparing, and adjusting is called an automated feedback loop. If you can explain the ADC to microprocessor to DAC flow, you are guaranteeing yourself top marks. Section 6, Acing the Hardware Exam, Strategy Execution. You understand the hardware now. You know your von Neumann architecture from your embedded systems. But how do you prove that on exam day? Let's fix Alex and Sam's mistakes. Imagine the exam question asks, discuss 4 ways to improve the performance of a CPU. This is exactly what our student Alex would write. The performance of a computer can be improved by using more RAM, changing the clock speed, and using bigger buses. Why is this a flawed, low-level answer? Because while it states factual computer science terms, it completely fails to explain the mechanism. It's like saying a car goes faster if you put a bigger engine in it without explaining horsepower, torque, or aerodynamics. Alex is just listing things. You will lose points here because you aren't showing the examiner that you actually understand the underlying architecture and how these components interact. Now watch this transformation. Contrast that flawed answer immediately with this high-level answer taken directly from the examiner's guide. Look at the difference in depth. Increasing the size of RAM, since data is constantly moved into and out of RAM, the larger the RAM, the fewer data movements there needs to be, which increases operational speed. This student doesn't just drop a buzzword. They use the Peel framework. They beautifully expand on exactly how the component physically interacts with the data to reduce bottlenecking. They explain the why. That is the explosive power we are talking about. That is how you secure top marks. So, distilling the examiner comments directly from the source material, here is your computer science success blueprint, your final system. 3 rules that guarantee top marks: command word decoding, Peel framework application, and the time management matrix. Rule 1, state the facts clearly based on the command word. Rule 2, you must expand on the why and the how. If you mention a magnetic field sensor, explain that it measures changes in magnetic fields to detect rotation. Rule 3, discuss the effects. If a question asks about clock speed, don't just say, make it faster. Explain that overclocking risks overheating and desynchronizing that fetch, decode, execute cycle we talked about. And always use specific terminology. Don't say the computer holds data. Say the memory data register temporarily stores the fetch data. Listen, students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly explainer videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams at acetheexams_IGCE to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCE and click that bell. Don't let another exam pass you by. We have covered a massive amount of ground today, from the microscopic buses inside a CPU to the massive automated control systems running chemical plants, and finally, how to decode the exam paper itself. But I want to leave you with this final thought to take into the real world. The hardware we studied today isn't just theory hidden in textbooks. It is literally the invisible nervous system of our modern world. So take a second. Look around the room you are sitting in right now. How many hidden embedded microcontrollers, invisible infrared sensors, and automated feedback loops do you think are quietly monitoring and controlling the space around you right this very second? It's mind-blowing when you really think about it. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.